y'all. Thanks for ruining what would otherwise be the most triumphant Thursday to show up and listen to some math. Crying out loud. Let me tell you what the ground rules are. This talk will be, this is stuff that you all can do at home with a handheld calculator as well. Maybe the last thing you can't do with a handheld calculator. But I'm going to talk about large numbers. Feel free to jump in at any time. Thank you all for inviting me. I've given a lot of talks in the past couple of years in particular, and this one I think I am the most proud of. I am very honored to be now part of this great tradition that you all have here at Eureka, so I'm very grateful for this opportunity. Let me start off with a clock. Ever seen one of these? How many of you have ever played with this? Right? Well, I'm not going to go into that. That's a whole other lecture. So if you're ever looking for another one of these to talk, I can talk forever about the actual mathematics on this. But I want to do something simple. I want to count how many ways there are to arrange this. So one of the things that I can do is, how many of you have ever solved this? How many of you cheated? What's the best way to cheat? No, don't do that. The stickers never go back. Take a screwdriver and pop it apart. That's the best one. So if you pop this apart, on this Rubik's Cube, there are, well, two kinds of things. If you take this apart, you will see that it's got a skeleton that are basically three mutually perpendicular axes with the faces on it. And that's there like a skeleton. It never moves. You've got two other kinds. You've got these kinds that I'll call corner pieces that have three colors on them. And there's 8 of those. And then you've got these side pieces that have 2 colors on them. And there's 12 of those, right? 4 across the top, 4 across the bottom, then you've got a belt across the middle. Okay. Now, suppose that I'm going to cheat. And so I take a screwdriver and I pry this thing apart, and I've got pieces all over the table. I got some corners, some sides, and I start to put it back together, but because of my sinful ways, I'm stricken blind. And so now I am just fitting pieces back, right? So now I can't see the colors anymore. I'm putting this back together at random. So, one thing I know for sure is when I take one of these pieces with 3 colors on it, I can't cram it into a side place. There's only 8 places to put it, right? So I'll pick up my first corner and I put it somewhere, and then the second, and how many choices do I have for putting the first one in? Well, I've got 8 slots. And I pick up another one, I got 7 slots, and 6, and so forth. So that gives me 8 choices for the first slot, 7 choices for the second, 6 for the third, and so forth. And finally, that last corner, there's only one place to put it. This is, how many of you have seen that notation? This does not mean 8. What this means is, for any integer, you go n minus 1, n minus 2, all the way down to 1. Right? I'll use this as a shortcut because this is 40,320, right? And it's much easier to write this. So, geographically, I can put my corners in that hand. And then, of course, I start putting the sides in, right? And the first one, I've got 12 choices, and then 11, and then 10, and so forth. So, I'm up to that many. But it's even worse. Right? Because, let's go back to putting in the corners. Geographically, I can put this piece right here, but there's 3 ways to put it in there, right? This is yellow up, but I could have put it pink up or blue up, right? So for each of the pieces, there's 3 ways that I could have screwed it in. So that's another 3 to the 8. And of course, every one of the sides goes in 2 ways. That's the number of combinations there are on the cube. If I put it together blind, here's a question for you. Suppose that I did put the cube together blind like that, and I gave you the cube, and I make a bet with you. I hand you the scrambled cube, and I'll say, I'll bet you $100. I'll bet you $100 that you can't solve this. And you can look on the internet. You can't solve it without taking it apart again. Should you take my bet? Let me sweep it for you. I'll give you 10 to 1 odds, right? If you can't solve it, then you owe me $100. If you can't solve it, I owe you $1,000. You know not to bet with mathematicians. The answer is you shouldn't take that bet until I give you 11 to 1 odds. If you assume it at random, and this has to do with $2, can't talk about it today really, but there's a 1 in 12 chance that a cube assembled randomly can be resolved without taking it apart again. So here, don't ever say I never gave you anything. When you cheat on the cube, put it back together correctly. So the number of combinations is actually this divided by 12, which is 11 factorial times 8 factorial times 3 to the 8 times 2 to the 12, which is about 4.3 times 10 to the 19. That's about 43 quintillion. So how big is that? Right? You know, it's funny because I bought a bunch of cubes. I taught this in governor school a number of years in North Dakota. And when I first moved to Fargo, you could not find a Rubik's Cube in any toy store. And so I went to the best toy store in town and I ordered 25 of them. What, are you crazy? But I had to order all these cubes for governor school. And I changed the Fargo markets because within 2 months you could buy a Rubik's Cube in every store in Fargo. So I know they spy. But the box that the cube came in said, Rubik's Cube, billions of combinations, only one solution. You will never see such grossly over-the-top advertising. I mean, isn't that what advertisers do? Right? The guy that sold me my car that's basically a McDonald's dumpster with a motor in it said this is going to be the greatest thing in the world, right? They're supposed to embellish. They say billions of combinations, one solution. It's got 43 quintillion. And this is a number that I made really easy by using just a few numbers, 4.3 times 10 to the 19. Well, let me give you some perspective on the size of that number. If you give a Rubik's Cube to all 300 million people in this country, all of them, and put them in a big row, give them the cube, go. And they all start scrambling the cube. And every one of those 300 million people gets a different combination every second. Nobody does what anybody else has done. Nobody repeats anything. They're all getting something different. All 300 million, every second, 24 hours a day, for 40 years. And you have a computer, and it records all those combinations. At the end of that 40-year period, you will have 9/10 of 1% of the number of combinations. This is a big number. I want to play a couple of games now. Some of you have probably seen this. This is my attempt at a chessboard. I want to play a game on this chessboard. And the game I'm going to play is I'm going to start putting checkers on there. Now I'm going to use a checker that's a 1/4 inch thick. My brother and I used to have a plastic checker to play with, 1/4 inch thick. And I am going to start right here, and I am going to stack 2 checkers, and then 4. So now we're 1 inch tall, right? Because they're 4 inch stacked. And then a, and so on. You guys see the pattern? 2 to the 64. See the number of checkers. And the last checker. Once I fill this up, my question is, give me some perspective on how tall that stack of 2 to the 64 checkers, each at 1/4 inch tall. Anybody want to take a? You want to? Anybody would be great to take a stab at it? No takers? What do you think? Where did I come from? South Carolina. Think it reached South Carolina? Pluto. Okay, he's covering his bets now. For me to tell you how tall a stack of checkers is, how many of you know what a light year is? right? A light year, for those of you that may not know, is a measure of distance. It measures how far light travels in a year. Now, light travels 186,000 miles per second. That is 7.5 times around the Earth at the equator every second. That right there is how much light travels in a nanosecond, a billionth of a second. Okay? Give you some perspective on the light distances. Our sun is 93 million miles away. That's about 8 light minutes. Right? So if the sun blew up 4 minutes ago, we got 4 more minutes to party before it's all over. Right? So, that stack of checkers is 12.4 light years long. So that actually reaches to the nearest star and back and then back. So if you're at the bottom of that stack of checkers and you turn on your flashlight and I'm at the top of it, I'm not going to see your beam of light for 12 years. Now, let me ask you this. I've got this calculator. My secretary actually gave me a calculator when I left to go here. And this is like second generation calculator, right? It's like the kind my dad. I used to go in and play with my dad. My dad's an architect. I would play with his calculators sometimes I was a kid. And so I remember the number 69 because in the old calculators they couldn't do anything over 10 to the 100th power. It was stuck right after that. And 69, if you push the little factorial button, gives you a number. And 70 factorial, it gave you an error because it was actually over the 10 to the 100. They couldn't go any farther. Let's play the same game with checkers with factorial. 1 factorial, 2 factorial, 3 factorial, so that's 6 checkers. And I get down here 64 factorial checkers stacked. My question is, what do you think about that stack of checkers? Who's bigger than the bigger than the other one? Yeah, 64 factorial. But let me preface this with saying 64 factorial is in the safe zone. Even if my dad's old primitive calculator, it would compute this number. How many of you guys know what the Andromeda Galaxy is? Right? You guys have seen it. It looks like a big fried egg, right? Pictures of it. It's the sister galaxy to us. It is 2 million light years away. So, like I said, if it blew up 1 million years ago, it's still 1 million years before we see what happened to it. That stack of checkers will reach to the Andromeda Galaxy and back 21 billion, 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 billion times. In fact, you'd never be able to prove this about it because there are more checkers in that stack than there are subatomic particles in the universe. So we would need to borrow other universes to build the stack of checkers. Okay. The last little kind of warm-up that I want to do has to do with Google. And I don't mean looking for stuff on the internet. Actually, this. How many of you are familiar with this terminology? Right, for those of you who don't, this is just a shorthand for this number. It's the smallest number that my dad's old calculator. And it's 10 to the 100th power, or 1 followed by 100 zeros. And so this is called Google. My girlfriend up in Fargo had a bunch of books, like these kind of kid books, to try to get her kids all excited about math and various things. And she had this one book about making math friendly. And I used to love the books she had. They were kind of fun. And the author, wrote all kinds of interesting things about math and, getting people all worked up about math. It was very good. But one of the things that he said was people asked him what a Google was, give him an idea of Google. And he said, to impress his audience, he would say, a Google is the number of raindrops that have fallen in Scotland in the past 100 years. And I remember laughing at my girlfriend when I read that. Maybe that's why I'm kind of my girlfriend. Anyway, I said, the author is correct. He's correct. But for sure, this is an understatement. So I actually did computation. And the area of Scotland is about 30,000, a little bit more than 30,000 square miles. I rounded up to 32,400 because that's a perfect square, and I'm way too lazy now. So I computed the number of square inches in Scotland, and then my next task, and I messed this one up a little bit, but my next task was say, well, I want it to rain hard all the time. So I assumed that it rains all the time in Scotland, and every second you get 200 raindrops per square inch. I checked this fact tonight. Actually, it turns out I did it a little bit, because in a cloudburst, you tend to get about 113 raindrops per square foot. So basically, you would drown in my rain. Right? It's like standing in front of a fire hose. Okay? But you're getting like 200 raindrops per square inch per second, raining all the time. So the question is, how long at that rate will it take for a doodle of raindrops to have fallen on Scotland? It's more than 100 years. In fact, it is 870 billion times the age of the universe. And I mean the age of the universe from the Big Bang Theory, not from what I learned at school in Tennessee. Okay. So I want to kind of change some thinking a little bit, because I'm going to leave you with kind of one last problem, but I need some. So here's the participation part, young. I'm going to ask some questions now to maybe show you the thinking about some probability equations. How many of you have ever seen a TV show? This is actually a rather famous math problem right now. Some of you may have heard of it. Have you heard the GOAT problem? Have you ever heard of this? Well, how many of you are familiar with the TV show Let's Make a Deal? Right? Some of you, I think they still run it, don't they, on some of these game show networks or whatever. Well, what would happen is there will be 3 doors, and behind, here's the facts that you do. Behind one door is something that you want, a new car, right? And behind the other 2 are something that you don't want, like goats or something, some dad prize like this, right? So one of these has a prize, the 2 others junk, right? And of course the game show host knows where the prize is. And so what would happen is the contestant would step up and the host would say, which door you want? Well, I want door number 1. And then the game show host, who knows where the car is, would then, to increase the suspense, open one of these 2 doors, because one of them has to have a goat in it, right? I mean, maybe they both do, but at least one of them. And he would open the door and show the goat. And then ask the contestant, okay, here's your chance. You want to change doors? Now, here's the question. Should this person change doors? Or does it make any difference? You know why? You know why? You actually double your chances of winning by changing the door. And here's why. Here's the way and this is going to help us with our thinking with the next problem. Suppose that I am Mr. Stubborn, and Mr. Stubborn never changes. Okay? I don't care what the game show host, what he shows me, I'm never going to change. I am always going to go with the door I picked. What are my chances of winning? 1/3. I've got to do it right the first time. Agreed? Now, what if I'm Mr. I always change? What happens if I guess wrong the first time? What happens if there's a goat here? One of these two has the card. The game show host has to show me this one that has the goat with it. If I change, I win. Right? So if I guess wrong, I win. You guys follow that? So what are my chances of guessing wrong? 2/3. So I will double my chances of winning by changing. Do that experiment with your friends. You can win the barbells on that. You know, I feel like this is such a cheat. Richard, did you get a head count from me? Was it? That's too much of a cheat. How many do we have in the middle here? 5, 10, 15, 20, 25. Yeah, that's about right. I tell you what, I've got, let me do this, 5, 10, 15, 20, 25, 27, 30. There's about 35 of them here in the middle. Let me ask you a question. That's about, what? That's about 1/10 the number of days of the year? My question is, what do you think the chances, you guys out on the outliers who just watch this, what are the chances of these two get the same birthday? And I don't mean same day of the year, I mean just same day of the year, not day and year. What do you think? There's 35 of you. Do you think the chances are good? 1/10? 10%? Well, let's try it. Actually, let's see. Here's what I want you to do. As I point you out, just holler out your birthday. If anybody else got that birthday, stop me.
What's my over?
13th July.
June 8th.
March 15th.
This 24th.
January 26th.
February 16th.
February 4th. July 24th.
August 16th.
May 1st.
August 8th. July 3rd. January 20th.
May 29th.
June 24th. July 12th.
January 26th.
December 28th.
We have the same birthday.
There we go. Actually, I've never been beat on this. But I was getting a little nervous there. Actually, by the time you hit 30 people, it's over a 70% chance, right? And actually, it's even better. So I'll give you the stats. At 23 people, you got a 50-50 chance. At 27, you're over 60%. At 30, you're over 70%. At 40, you're at 89.1%. At 50, you're 97%. And at 60, and this is why I didn't take the full room, at 60, it's 99.4%. Right? And that also assumes that there is an equal probability of having birthdays every day of the year, which is not true. Their babies tend to be born 9 months after Valentine's Day and things like this, and that clumps the odds even more in my favor, as a matter of fact. So, why is this true? I mean, does that surprise you that if I got 23 people in the room, there's a 50% chance that at least 2 of them will have a birthday? I think that's a little bit surprising, isn't it? But here's the way that we have to think about this. Trying to count the number of ways that you guys can have the same birthday is too hard. There's too many things that happen. You 3 might have the same birthday, or you 2 might pair up, and you 2 might pair up. Any of those situations, I win. I win my little bet, right? What's the way that you win your bet? Nobody has the same, right? So let's think about it this way. Think about putting these people in a room one at a time. Very thin people. And the first one comes in. What are the chances that this person, his birthday is repeated? None, because there's nobody else in the room, right? Okay. Now bring in the next person. What are the chances that you guys continue to win your bet? Well, he's just got to miss this birthday, right? The chances are good of that. 364 out of 365. Now bring in another one, right? What are the chances that this guy is a new unique birthday? Well, he's got to miss these two, right? 363 out of 365. Next one in, now he's got to miss 3, right? And notice what's happening to this number, right? Now, this number starts pretty close to 1, right? I mean, 0.99, something like that. But if you guys ever, what happens when you multiply two numbers that are less than 1? What happens when you multiply 0.9 by 0.9? What do you get? 0.81. I mean, that falls rather significantly, right? Now, these numbers are a little bit bigger, so they don't fall quite as significantly, but you're multiplying a lot of them, and they're starting to get even smaller, right? So actually, this number, as you add more factors to it, as you keep bringing people in and having to multiply new numbers, this starts pounding down pretty small. Now, what's the chances that I get this bet? Well, if you bring a bunch of other people in here, and we'll call this n for number, and multiply these all out, this number gets very close to 0 pretty quickly. What are the chances that I win the bet? I win the bet if you don't win, if any other thing happens. So the chances that I win is 1 minus n. But if n is very close to 0, then it looks like I'm going to win this out. And like I said, you can do this experiment yourself, but the numbers start falling very quickly. So by the time you've got 23 of these people in the room, you've got a 50-50 chance, and it starts falling fast from there, as a matter of fact. Okay. Any questions? Okay. So now I am going to embark on probably the last kind of big number problem that I'll show you. And then we can take questions and whatever. But this one will require a little bit of setup. Okay. Now what I'm going to do is, the first thing I'm going to do is ignore the curvature of the earth. So we'll do that. I am going to dig a cubical pit in the earth, and very flat. It will be 1,333 miles this way, 1,333 miles this way, 1,333 miles deep. It will be very hot at the bottom of this pit. And the width of it would reach from here to Florida. Okay, this is a big pit, huge pit. And in this pit, I'm going to put a whole bunch of little cubes. I'm going to fill this top to bottom with little, they look like little dice, only a little bit bigger because they're 1 inch cubed. And I'm going to fill this pit up with these cubes from top to bottom. All of them are white, one of them is red. So in this vast sea of dice, there is somewhere a little red, 1 by 1 by 1 cube. And I take you, and I put a blindfold on you, and I toss you in the pit and say, pick one of these around, right? And in fact, you can dig anywhere. I pretend you're a ghost, so you can move up and down through it, however you can get there. But you pick out any cube you want, blindfold, and then you show it. What are the chances that you get it right? Not good. Right? I think we can agree on that. Not good. By the way I designed this particular problem, how many of you know what Avogadro's number is? Right? Chemists for sure will know this, right? It's It's a big number. It's bigger than Rubik's Cube number, right? This is designed for the number of little cubic dice that fit into this big pit I dug in there is about Avogadro's number. That's how many fit. That's what it's for. So we can all agree that you've got one chance in 6.022 times 10 to the 23rd. Not good odds. Agreed? Okay. I agree. Now, I'm going to do the following exercise. I am going to assume that ink molecules are the same as water molecules for purposes of weight and mixture. I'm going to take a mole of ink, which is very small, it fits a small vial, and I go, and my vandal self throws it in the ocean, ink. And I wait 20 years, and I assume that the ocean, all the oceans, mix this ink uniformly throughout the ocean. 20 years later, I'm cooling my heels in Hawaii, the dream, and I step into the ocean, and I take a glass of water, put it in the ocean, pull it out. What are the chances that I have at least one of those ink molecules that I've dumped in the ocean 20 years ago in that glass of water? Huh?
Very first one.
Yes. What are the chances?
Good.
Let me help you. Let me help you. This is what I designed it for. The distribution of the molecules in the ocean is the same density as that one red cube inside the 1,300 by 1,300 by 1,300 miles. That's about the same density distribution that you would have. So you dip the water in, what are the chances? It would cease. It would cease. But actually, it's almost certain. So here's how to think of it. And I don't want to write all the numbers, I'll write the numbers later. But in number of molecules of water in ocean. And I'll show you what I did, because this has an interesting correlation. And A equals Avogadro's number. Now, A number, I don't know how to spell Avogadro, sorry about that. Now, when I dip the water in, don't think of me taking the full cup out. Think of me doing it as follows. Think that I've got very tiny, delicate fingers, and I fill by putting in one molecule at a time. Okay? This will be a long process, but it's the right way to think about it. So imagine that I'm putting in one molecule at a time. This is just like the birthday problem, right? Because I asked, what's the probability that there's at least one ink molecule in there? There could be 2 or 3 or 7 million. Who knows, right? The only way that there's not at least one is if there's absolutely none, right? So that first water molecule you pull out, A is the Avogadro's number. N is the number of molecules in the ocean. After I add A to it, that's now the number of molecules in the ocean, and I've added those. Now, this is like 10 to the 23, and this is 10 to the 46th, right? So this is just a very small difference, right? This is a fraction that is a little bit less than 1, right? Because that denominator is a little bit bigger, but ain't much. I mean, this is so close to 1 it stinks. But I go through this process, it's like, okay, the chances are really good, I don't get it. And then, look, I even did this. I'm subtracting molecules from the ocean here. I feel like a complete idiot, right? Oh, look, I took a molecule out. Etc. Remember the birthday problem? I've always got to be getting water molecules, and that's the only way to do it. And finally, the last one, n minus A over n. Now, that's what it takes for you to win, because you've got to pull water molecules every time. That's the probability that you win in nothing in there at all. Right? Now, the first question I might ask is how in the heck would you even do this computation? Because this dot, dot, dot is a general euphemism, right? There are 6.02 times 10 to the 23rd terms here, right? And these are so big that they can't be handled very well, even by very, very good computers. And even if they could, multiplying all these parentheses in the numerator alone is about 2 to the power of 6.02 times 10 to the 23rd computations. It can't be done. The universe will end first, right? And that's not an embellishment. So the first thing I did actually, it was to estimate. And I cheated like nobody's business by doing this. N over n plus a to the a power. This number is actually a bound to go on because actually what it's going to do is it's going to underestimate my answer. The real answer is going to be much more striking than this. And this is hard to do too, because it's hard to take 6.02 times 10 power. So how would you handle this? Well, you might take a log of it. So you could do something like take a logarithm of it, get it, and then exponentiate it back to get it. And this is actually rather effective. But whatever this number is, chance of at least one ink molecule is 1 minus this guy. I'll call it number. Because this number generated is essentially, this is what it takes for you to only get pure water, and you get a pure water. Now these numbers are all very close to 1. Very close. So you wouldn't think you're changing much, but the fact of the matter is, multiplying something by itself that's not 1, 6.02 times 10 to the 23rd times is dramatic. This number comes out, and remember, this is conservative. There's about 99.98% chance that there will be at least 1 ink molecule in that glass of water that you got out. And this is very conservative because this estimate that I used is the actual answer will be, this number will be much smaller. I suspect that it's probably more like 99 point, probably around 20 times, something like that. It's almost a certainty that even though it's distributed, that, you know, it's the same as that 1 cubic inch in the 1,300 by 1,300 by 1,300 miles. Even though it's distributed like that, it's almost a certainty that that cup of water will contain at least 1 ink molecule. And, you know, think about that problem the next time you're sharing a swimming pool with some kid wearing a diaper. Okay, so that's all the new stuff I had. I've been honored, and I hope you feel like you got something out of this. I guess if there are any questions, I'd be happy to field them.
I was watching this on Nova last night about math, and they said that somebody calculated pi out to like 200 hours.
These are really more like computer science problems, where they're doing things with algorithms and stuff like that. Because actually, pi to just a few decimal places is more than we need it to very accurately calculate everything on the universe. But yeah, it's a theoretical interest too. I mean, actually, one of the most famous ways to compute pi actually is so there's alternating fractions, odd 1 over 1 minus 1 over 3 plus 1 over 5. If you multiply this by 4, you get pi exactly. And you can get pi more and more accurate by taking more and more terms, right? But this process converges very slow. This is one of the worst, it's the coolest way to get pi in a certain sense, because there's some elements to it. But computation is not very good, because it takes way too many of the terms to be practical. So oftentimes what they do is they come up with new ways to compute pi, and really they're testing algorithms and trying to do things. There was something I read on it. There's a formula for the nth digit of pi in hexadecimal, something like this, where you don't have to compute the previous digits, which is kind of interesting too. So. Did I answer the question?
Yeah, I was just kind of wondering about it, why do they do it?
Well, a lot of people mad at things because it's there. You know, it's the K2 thing. Yes, sir.
Just an observation that in the general chemistry class that I teach, there is the textbook, there's an example to give the students the sense of what the Avogadro number size is.
Oh, so they give some examples in the
Yeah, and one of them is that if you take the Avogadro number of baseballs, that's equal to the mass of Earth.
Right.
And if you take the Avogadro number of water droplets, it's the volume of all the oceans on Earth.
Yeah, so that's kind of the point, because I mean, it's very easy with the advent of easy computing and calculating exponential notation. It's easy to throw these numbers around without really having a good perspective on how big they are. There was a famous mathematician named Jean Genet, and he was funny because he said 1, 2, 3. This I understand. 10,000 is getting a little abstract, and it's true. It's hard to imagine 10,000 things.
So I'm wondering, how did these people before, I mean, eons ago, how did they come up with a gravitational constant or Planck's constant or Avogadro's number? How did that number, how did they arrive at that number
Experimentation.
negative to them?
And of course, I mean, some of the ancient Greeks did some of the volume philosophies, or volume formulas, and they did a lot of by experimentation, and I mean, this was before the calculus, and so they had to do other sort of clever techniques to figure out polygons and things like that. But people are very, very clever. Actually, I forget the name of, I think it was an Egyptian, but he noticed, this is terribly clever, he noticed that at noon in a certain city, that at noon the shadow would be, he could measure the shadow on a stick that was standing up. He also knew that in another city that was south of them, at noon the sun pointed straight down the wells. And so what he did was he paid somebody to pace off the distance between the two cities, and he assumed that it was curved, and to a great degree of accuracy, he determined the circumference of the Earth. Right? So humans can be clever beings sometimes.
What about the debt? That's another big number, so for like Greece and the United States and Illinois and places like that, how do they calculate all this?
Yeah, they don't know what you're talking about. Plain and simple.
They just don't, they probably don't.
Well, they don't know the I don't think that they really know the weight of the numbers that they're calculating from it. I mean, and of course you can, I'll never forget that, I guess in chemistry, you can correct me if I'm wrong, but actually what we call a calorie when we eat is actually a kilocalorie, but it's really, we just call it a calorie because nobody goes around and say kilocalories all the time, right? And my 8th grade teacher pointed this out to us, and a bunch of people freaked out, like, oh my God, I've got to stop eating, right? Because I'm eating 1,000 calories every time I eat an M&M. And it's like, we don't really understand numbers here either, do we? Right? Because it's all a matter of scale, too. Right?
Actually, in England, they use kilocalorie.
Oh, okay. Yes, ma'am.
So how did you get interested in figuring out big numbers?
Oh, I just did this for fun. And my research is actually something else, but I just said, I think I probably got interested in doing this just because I used to be mad at my dad's calculator for not going past 10 to the 100. You know, and I would see people throw around these numbers, and, you know, it would be fun to, and I also used to come up with some examples just to keep my 8 a.m. calculus class away, because people sometimes like to see real concrete things with me, so. Yes, sir.
I have a question. A couple of years ago, I was preparing for a talk, and I was throwing some back of the envelope calculations to give some examples. And the information I was looking for is an estimation of the total number of people that ever lived on Earth. So I don't know a way to calculate that. So I went to Google and looked for, and I saw different estimates, different numbers thrown, and one number that I found was 100 billion people. Now, and then I thought, isn't that too small? Because the current population of Earth is about 7 billion people. So 100 billion is just a few times more than that. So, and we have
Yeah,
been
but for a
around for so
long period
many
of time,
thousand
the planet
years.
had a relatively small population. But of course, you know, here's the thing that,
Oh,
here's the
just
thing that's
wondering
certain.
if this is
It took 2 people to create it. And those 2 people took another 2 each to create. So now we're up to 4, and then 8 great-grandparents, blah, blah, blah. And you don't have to go many generations back before you look at the total number of your ancestors is more than the number of people that have ever lived. And so those branches aren't all separate, for sure. Yes, ma'am. What's that? Yeah. Oh yeah, yeah. I was taught evolution. Yeah, in the public schools of Tennessee, which is really surprising. I actually graduated from an uncredited high school, so it was in my county at the time. We used to have a joke that Tennessee at the time was 49 out of 50 in education, and we always said, "Thank God for Mississippi." And out of the 95 counties in the state, I'm sorry about that. That's the way it looked. And out of the 95 counties in the state, my county was 94. And we always said, "Thank God for Cobb County next to us." Yes, sir.
What is your problem with my golf ball? The Let's Take a Deal problem? I seem to remember there was some controversy when that was introduced in Parade magazine.
Yes, yes, yes. And actually, Marilyn Beau Savant was a little bit disingenuous on that, because in the first article where the problem first appeared, she didn't really make all the parameters clear. And I think she kind of hoodwinked some people and then just kind of pounced on it, which was, but I mean, what she said was correct, but I don't think she was completely lucid about what the rules were. That's why I was careful to say that he always must open the door with go and blah, blah, blah. Yes, ma'am.
For the numbers that are up there for like the pi problem, as you continue putting up terms, do they go by just like by odd numbers or is it by primes?
Yeah, that's a great question. Odd numbers, right? The next number will be 190. Right. Yeah. And if you notice, they're all prime. Very nice.
Is there any other questions for our speaker? Well, let's thank him for coming. If you want to join us for a little reception.